All right. So we talked about the electron double slit experiment last time, and how as we observe the electrons, they always show up as particles when we observe them. But when you look at the distribution of the electrons, you get an interference pattern when they pass through both slits. And we spent quite a bit of time discussing the weird aspect of it, which is when we observe the electron by, say, shining light on it or whatever other method you may choose to use to figure out which slit the electron went through, then the interference pattern disappears, right? And in fact, as we saw in the last class, we came up with various ideas for like how this might be happening. But we were always timing, because there's usually something about the experiment that shows you that you can't get away with that. And one of the main reasons, as we talked about, is as soon as we make a measurement on the electron that tells us where it's located by the uncertainty principle, we are prevented then from observing the interference, because the electron gets a kick that is so big that it washes out the interference pattern. And then if you don't observe it sufficiently small so that we only give it weak kicks, then we can't tell where it is. And so then again, we lose the resolution to know which slit it went to. And all of this can be explained using, I've already talked about the postulates of quantum mechanics. I didn't talk about the uncertainty principle because it actually follows from these postulates. So it's actually one, although we refer to it as a principle, it can be sort of derived from these postulates of quantum mechanics. So, but it's certainly a valid law or principle of quantum mechanics that you have to respect when you make measurements. So I thought this may be another topic. How many have heard of this experiment, the delayed choice quantum eraser experiment? Nobody? Oh, okay. Let's talk about it. And maybe since you've never heard of it, you may not be so puzzled by it. The people who have heard of it or have seen YouTube videos about it are often very, very confused by it. And that has to do with the fact that many of the YouTube videos out there are pretty bad in the way they cover this topic. So let me stop the share. Okay, so in the class we were talking about, we have slit 1, slit 2, we have a gun with electrons that shoots electrons through, both the slits, and then we observe over here with a detector, an electron detector, and that signal is plotted as a function of, as we scan the detector across the screen, or we can just think of the screen as having an infinite set of detectors on it that record where the electron was positioned when it hit the screen. Okay. And we talked last time that we can have a source of light, and that light might scatter the electrons, be on a detector, scatter the electrons from here and be on this detector. And so then knowing which detector, let's say I call it D1, D2, that will tell us, which slit it went through, and that was how we talked about what happens when the photon has sufficient intensity or insufficient intensity, or if it has when the light source has too much intensity, then there's like a lot of photons. That's obviously going to disturb it. But even if you reduce it down to 1 photon, then if the energy of that photon is sufficient to disturb the particle, the electron, and the energy, of course, as we talked about, is given by the wavelength, right? The wavelength of the photon gives it the certain energy and momentum. H over lambda is the momentum. Energy is H times F, as Planck discovered, and was also realized by Einstein in his photoelectric effect. So all of that means that the photons are kicking the electrons around, and that is what leads to the loss of the of the superposition that we observe, the fringes, the interference fringes, right? That's our main thing that we had explained, interference fringes. Okay, so another way, maybe more modern way of talking about it, which I'll introduce a little bit of notation, hopefully it's not too scary, is let's call this slit 1, slit 2. And we can say that the electron is either in slit 1 or in slit 2, right? So this is just a notation for the state vector. In quantum mechanics, as I mentioned, everything is represented by a state vector, and the overall state of the system. In this case, the state of the system can be in one of two possible states. It's either in state 1 or state 2 when it's observed, right? And the overall state psi of the system must be some combination of 1 and 2. Okay, so mathematically, we could write it as some A times 1 plus B times 2, right? So let's just, take it as like a mathematical formula or fact that we can write it as this relationship. In fact, we can go, let's say A and B are equal and are 1/2 or 1/√2 actually, as it turns out, but let's just, for now, we don't care about all those facts of like the actual numbers. We're just saying it's in some superposition of 1 plus 2, okay? And the idea of like quantum mechanics is that we have discussed a little bit is that this is called which way information, which makes sense, right? That is the fact that we know whether the electron is in state 1 or state 2, that is a which way information. And as soon as we have which way information, this superposition collapses from this into one of the states, 1 or 2. Right? That is kind of our model of quantum mechanics. The measurement of the state of the system being in 1 or 2 changes our knowledge of the wave function from being in this unknown state, which is a superposition. It's unknown only in that we don't know whether it's in 1 or 2, but we know it's in a superposition between 1 and 2. Okay? And the measurement makes us discover or realize that it's actually in 1 or 2, and that's the which way information, which is given by the photon, for example, scattering of the electron and recording a click or a signal in detector 1. So when we get a click in detector 1, which means the photon bounced off the electron here and went up there, that tells us that the electron went through slit 1, and therefore we can now say that the superposition has collapsed into this which way path or which way information. As soon as we have which way information, the interference fringes here, which were there, now collapse into this broader, just a distribution which is located around that slit 1, right? So that is an important sort of principle of quantum mechanics, that whenever we have which way information about a superposition, which way just means that we have some information about, which of the many paths that the electron could have taken is what actually happened. Like if there is some knowledge about that, then we can no longer get interference, we can no longer get these weird wave-like effects, if you like, okay? Okay, is that clear what I mean by which way information? The analogy with the slits is why it was called. It's called which way information. But this which way information doesn't have to be necessarily even recorded. Okay. For example, if as we know, this photon was scattering off of the electrons, right? So we could also write the photon as having some state. Okay. So let's say that the state of the photon, right, is some state. So the photon has some state. Let's call it D1 or D2, right? So those are the two paths that the photon can take, one that goes into detector D1 and one that goes into detector D2, okay? And then the overall state of the system, so imagine that we know that the electron went through path 1 and the system then recorded a photon in detector 1. We know that one way in which the system could then be written is 1 D1, right? So now I'm writing two separate states for each of the particles. So this is particle 1 is the electron. I'll put a label here. Particle 2 is the photon. Okay. So particle 1 is the electron, particle 2 is a photon, and then we have another state of the system, which is the electron goes through the slit 2 and the detector 2 clicks for the photon. So we have two separate states. Now the system, as we have maintained it earlier, the system, all we cared about was the electron, so I just wrote 1 and 2. But as soon as I broaden my definition of the system to include the photon, now obviously I have more states, right? I could also have a state, for example, we should not ignore this, where 1 and then D2, right? That could also be written down, right? That the detector 2 clicks, even though the slit that the electron went into was 1, for example. And obviously the other one, which is 2 electron detector D1, right? I'm going to drop this electron photon subscripts. Just the first one is going to be the electron, the second one is going to be the photon, just as a thing, okay? To make the notation convenient. Now, as I said, if you're a good experimentalist, you'll arrange it so that there is no chance that we ever get this state, right? So this state we preclude from the consideration because of the way we've set up our experiment. We are a good experimentalist. We make sure that a photon that bounces there can never make it into detector 2 and so on. Okay. So now the overall state of the system that I would have to write it is some linear, is some superposition of this system now. Okay. And now, as I said, now there is some which way information, right? The fact that, you know, the D1 and D2 is there in the system, right? Is recording some which way information. So it's not necessarily that I record it, that I even measure the clicks in the photon. If I look at if I make a sufficiently strong measurement, that photons that are coming from my light source will end up in D1 when the detector, when the electron goes through detector 1, slit 1, and photons that scatter off 2 will go into detector 2, then by my earlier argument, there is some which way information in the system. Even if I am not recording those clicks, the state of the system is now governed by this D1, is going to now be in one of these two states, which means I will lose the interference pattern at the screen. The screen interference will disappear as soon as I have a system where I've set it up so that the photons will definitely click when the electron goes through slit 1, and the photons will definitely click if the electrons go through slit 2. Okay, so there will be a loss of interference. Okay, in this, so this is an eraser. I have erased the. Sorry, I'm not yet erased. I made this into a classical system, effectively, right? So you can think of these photons as like an environment or some other variable that we are recording. Okay, so let's back up a little bit, and instead of, because with the photons, I'm introducing yet another particle and all that. So let's do something a little simpler than that. Okay. So let us imagine. So this is one. Okay, is this clear to everyone? What I'm talking about? The fact that we have the photons scattering off of the electron at all. It doesn't matter whether I count them or don't count them or look at the clicks. As long as I have this interaction going on with the system between the electrons and the photons, once I have that, then I'm guaranteed to lose the interference fringes at the screen. Okay. Now, okay, so that is my main claim. Okay, so it's a little bit hard with this because actually to fully explain the quantum eraser experiment, I would have to introduce entangled photons into this experiment. So let me not do that. Let me introduce a slightly separate version of this experiment. Okay, so instead of photons, I'm going to take the idea of it is still the which way idea is still there. I'm going to assume that when these electrons go through the system 1 or 2, okay, they interact with some recording element. Okay, the recording element can be another electron. Okay, it could be another photon. It could be something. Okay, I call this just the recording element, recording qubit, if you like. Okay. What does this recording element do? Okay. So again, it does exactly like that. It's very similar to what I just wrote down. With the photons, of course, the idea is I could have as many photons as I want. So it could be like a very classical system. So it makes the entire system very, strongly interacting with the environment. With the environment here is the photons. By the way, the environment could even be the screen. Like maybe as my electrons go through the screen, they give a kick to the screen. And that kick to the screen tells us if the kick is more towards the top, it's this slit 1. If the kick is more to the bottom, that's slit 2. Then that's another way in which the electrons going through leave some information in the environment about which path they went. So that's why we have to be careful about those aspects as well when we set up this experiment. Okay, so now let's talk about what's happening. So the electron that's going through, I store that into a recording electron. Let's just for simplicity, I call this recording electron. And the recording electron, instead of recording position, I could also record it as a position of that recording electron. I'm going to record it into the spin of the electron. You have now read about the spin of the electron in one of those papers. I've also talked about it in the class. But spin you can think of as every electron has associated with it a little magnetic moment, like a little bar magnet. So an electron or any quantum object, most quantum particles have a spin. And for an electron, the spin is half. It's just weird the way it's set up, but ignore that for a minute. What it means is that the electron can only point in two directions. Okay, either up, let's say, or down. Okay. And let's say that I record it so that when it goes through the upper slit 1, this electron will be in the up arrow or up spin, or the down arrow, the down spin. Okay. Now I should be careful. The direction that I pick for the electron, up or down, that's arbitrary. Okay. I could have picked left and right also. So I could have written this as 1 and then right, and then 2 and then left. And this will come back to sort of haunt us in a minute. Okay. But for now, I'll just say that let's say that we pick this as our system in which we are recording the information. Okay. So of course, as you have now learned, the overall state of the system, psi, must be written as 1 times up plus 2 times down. Right? So this is our state of the system. And by the same argument that I just told you about, the one thing we can do with the electron that's a little bit harder than with the photon, right? And this is why I chose the electron, is I can store that recording electron. I can put it away in a box. And this box is carefully shielded. You can think of it as an atom, it can be an electron, whatever it is. But this object, this qubit, can be carefully stored and separated away from the environment. And in principle, there's nothing that prevents me from storing this for years, right? And coming back later to measure whether the qubit is in one or is in top or down. Okay, that's one of the facts of electrons that's a little easier to do than with photons. I could do the same argument with photons also, but it's a little easier to do it with electrons. Okay, everyone clear on that? What the second recorder element can do? Okay, again, by the same argument, now as soon as we have created this kind of a system, this is called, by the way, an entangled state. Okay, why is it called entangled state? It means that knowing that the overall state of the system, right? There is a information encoded into the state of the system that is shared between the two parties. The one which is the electron that's going through system 1 or 2, slit 1 or 2, and the other electron which is in spin up or down. Okay, it's just a way of talking about that. And this is a special type of information sharing, which is quantum, because it's a superposition between these two states, which is quantum in nature, and that's why it's kind of special. And we'll come back to why entanglement has some weird properties later on. But what you need to know is that this is an entangled state. Okay. And as I've just mentioned, once we have entangled the system with another object, a particle, or something in this strong way, now we no longer have the interference. So if I look on the screen here, I would not see interference, right? The interference would be lost because there is some, even if I never measure this electron, the information about whether the particle went through 1 or 2 is encoded somewhere in that electron, and therefore I am going, when I eventually look at that electron and measure whether it's up or down, I would have known which path the electron went through, the other electron, the one that I'm observing on the screen. And therefore, nature then will immediately create now a non-interference pattern, meaning a regular pattern like the one we would see from a diffraction from a slit. Okay, so the fuzziness will be there, but the loss of like interference will be there. Okay, there will be no interference pattern. Okay, so this is, so we have lost the quantumness. Okay, because we know which path the electron took. Even if we didn't measure it right now, we can always measure it at some point later on in time, and we will then know, and therefore nature forbids us from observing the interference pattern. Okay, but here's where the eraser comes in. Okay, so now we do the eraser. What's the eraser? It is erasing the which way information. Okay, what we're going to do is we're going to erase which way information. We remember I told you there was which way information encoded in the state, right? Knowing the state tells me that there's one or two which of those paths was taken. But now I'm going to erase that information. How do I do that? Well, remember I told you the spin particle, the spin of this recording electron. When I open up that box and measure it, okay, of the electron, I don't have to measure it only in up or down. I can measure it in left or right. So I measure the recording electron in the left and right bases. Okay. And I'll make all the math of this more clear later on. But for now, what you need to know is that right is a superposition of up plus down, and left is the superposition also of up plus down, but with a minus. Because remember, as I've said, the state of the system can be written in this Hilbert space, and that state can be any of these possibilities, okay, like which are looking like this, okay, and they have this special behavior like this. Okay. If I now do the math, I write down. So if from these equations, I can also write up as a linear combination of right plus left, right? I just add these two states together, right? I add the up and the down equation, okay? As soon as I do that, if I add them, then I get right plus left is equal to just up. So in this equation, I can replace up, right, by right plus left. Okay, right arrow plus left arrow. And similarly, if I subtract those two equations, so it's a very symmetric formula, right? When I subtract, I mean, ignore factors of 2, etc. That's all unimportant for us. Okay, so if I write our equation for psi in this way, okay, I just replace up with right plus left and down by right minus left. Okay. Okay, now I separate out the terms which have just the right arrow in them. So I have right, and I'm going to get 1 plus 2. Okay, and I have left, and I'm going to get 1 minus 2. Look at that. So if I choose, when I open up my box, not to measure in up or down, if I instead choose to measure in the right and left bases, right? So now you can see, right, when I measure in the right bases, my electron that went through the slits is now in the 1 plus 2 superposition. Which of course, remember, when it's in the 1 plus 2 superposition, I can get interference pattern. Because I don't know which 1 or 2 it went through. Similarly, if I chose to measure in the left bit, if I find the result, when I measure right or left, I could get either one with half probability. I can get either this one or that one, equal probability. Okay. So if I get right, then it went up plus 2, 1 plus 2. If I get left, I'll get 1 minus 2. Okay. But both of those are superposition, just a math difference of like plus versus minus. Okay. So now I'll recover an interference pattern. So I'll get that. When I measure the recording electron in the right or left, either way, whichever one I measure, whether it's right or left, now I don't know whether the original electron was in the up or down slit, or slit 1 or slit 2. So now I must have interference according to the laws of quantum mechanics. But now this is where the delayed choice comes in. Okay, this is quantum eraser, because what I've done is I've erased my which way information, right? Erase the which way information. But now I can do delayed choice. Remember, I told you, I put that electron into a box and I decided to make the measurement. I can make the measurement years later. Okay. Years later, I can make the measurement and then I'll get an interference pattern. Doesn't that seem weird to you? Because when the experiment was done, I didn't know what I was going to choose years later about whether to measure in the up or down or in the right or left basis. But years later, when I make that measurement and I go then and look at the pattern on the screen, I can now get an interference pattern. Whereas earlier, when I didn't look, I didn't get an interference pattern. I just got a broad, the broad, usual, boring, featureless background. Yes.
Okay, so the electrons stay on the screen.
Yes.
You get the two.
You record all the positions of the electrons during the experiment, right? Whatever electrons were here, you record all those positions. Okay. And all you do later on is you measure whether the recording electron was in the right or left. So what am I doing here? How can I now get interference? What is it that I'm doing?
You're making so you're not sure which one it went through.
Right. Exactly. I am. But I seem to be going back in time to do it, right? Because I have waited years later to measure which of these measurements to do. And I've recovered an interference pattern while originally, I didn't have the interference. What have I done? Yes.
Did you change the axis you measure on?
I did. That's what I have done. I have changed the axis that I measured on. But how did that allow me to recover interference when there was no interference earlier? We all agree that in the first experiment where I didn't look at the box, let's say I never opened the box just sat in a corner, like some of the boxes in my house. And later on, and I recorded all the positions of the electrons, we all agree that we should not see interference because there's which way information encoded in the wave function. Yes.
I guess you just deleted whenever you do it in a way where you still have the information, then in that box with the tracker electron, there's information about those particles and where they were going. And you can discern something. Whenever you switch it, no longer that information was never created. Right?
Information was never created. I'm not sure what you mean. Can you say that? I think you're somewhere going along the track, but I'm not exactly clear yet. But let me just listen to some of your friends first.
Is it possible to can you reverse so you go back to up and measuring and up?
Oh yeah, absolutely. Of course, once I make the measurement, it's done. I can't go backward because when a measurement is done, the state collapses, and I've lost the ability to I'll have to redo the experiment. Yes.
How did you replace the output spin with the right?
It's just the choice of which I choose to measure. Because remember, the measurement.
How did you make the up equivalent to right?
Okay, so this is the part of quantum mechanics I haven't told you yet, but I'm just asking you to take me on trust that when I have a qubit or a particle, I can choose which measurement axis to measure on. Right or left, up or down, that's within my choice. Okay? And the point that I was trying to make here is this is given by, again, because of the fact that the state of a qubit is this vector or the state vector in a Hilbert space, just like ordinary vectors, I can write, like a 45-degree vector, right, can be written as an equal superposition of the x and y basis vectors. This is just like that. Okay. The right vector can be written as a linear combination of the up and down vectors. Same with the left, it's just a linear combination of, so it's a state vector, just like you've learned about in other classes on vectors, they can be rewritten in terms of each other. Okay. That's what this I mean by this measurement along a different direction or basis. I mean, in some sense, the up or down is just arbitrary in this categorization, right? Up or down is just along some axis. And I can choose what that axis is. But the axis could be up or down, which is vertical, or I could say the axis is right or left. Okay. And I can choose the direction anytime I want at the end of the experiment, for example. Yes.
So when you measure the right or left
Yeah.
axis, you see the interference, but isn't like the interference corresponding to the up or down?
Interesting. But there is no interference with up or down, remember? Because in the up or down, the state is very correlated. Like knowing if it's up means I know it's in state 1. Knowing if it's down, I know it's in state. That's the which way information. What the eraser does is it erases that which way information. Right. Yes.
So it just puts it in terms of different state, like left and right, but you didn't.
I didn't record what?
Left and right.
I didn't record up and down. I recorded left or right.
Yeah, so that, because you're recording left and right, or you put it back in left and right, create the way.
Created the way. No, the experiment has been done already. I can't go back and redo the electrons again. But so like you have to think of this experiment as being done many times, of course, right? Because we're recording a distribution of electrons, right? Or I can think of it as a probability distribution for the electron, if I just want to think about one electron. Okay. But in the actual experiment, I would have done this many times. Each time I would get like a little box which has a recording electron. I would have not infinite, but huge number of such recording boxes, each of which corresponds to one of the electrons that went through the experiment. And then I would carry out this measurement. You first.
Okay, so when the recording electron gets put in the box, it's in up or down.
Well, no, I just said that it's like, I can write it as up or down.
Okay.
Yeah.
But then you measure it
Yeah,
as a difference.
exactly.
Okay, so
Yeah.
then isn't it
Very good. Yes.
the superposition you end up with, that's kind of fake.
Okay.
And you can reverse it
Uh-huh.
and get back to like up or down.
That's right. It is fake somehow, but then I have somehow managed to do something with it that seems to recover the interference. So what's the explanation for why I'm getting interference this time? But even though, as you said, it's kind of fake because it's just how I've chosen to look at this recording electron. So what is it that's fake about it is the question, right?
You can,
I mean, I told you I only looked at the right electron. Okay, and I got interference. Sorry, well, let me just catch.
Is it not that you're necessarily erasing the information, it's that you're just measuring different information?
Is it the fact that I'm not erasing information?
Because I mean, like,
I guess it depends on what you want to call it.
yeah, like conceptually, like, I mean, I guess you could erase information, but like, you physically can't erase.
All I'm saying is that I've erased knowing whether the particle was in 1 or 2.
Right, but like, yeah, so like,
And that should then give me an interference pattern. So
Right.
my claim is, and this is true, by the way, the experiments have borne it out. I'll give you some examples of experiments in a second. That when I choose to now, so what am I actually doing in the experiment is I've recorded all the positions of the electrons, right, on the screen. Okay. Later on, when I go to look at the box and I record whether I'm in right, whether the recording electron was in the right basis. And now I go back and I say, okay, I got a recording electron in the right basis. Where did the electron that hit the screen go to? And I construct the pattern of all the electrons that hit the screen whenever the recording electron went to the right arrow. Okay. And then I get an interference pattern. Does that make sense? How the experiment is actually done, right? So I correlate, basically. I correlate the measurements of the electrons on the screen with the measurements of the recording electron being in the right or left. Yes.
So. I just, it's a fake, it's.
Yeah.
It's you're
It is fake.
changing the axis, so you're changing the variable,
Yeah.
so you're getting a different thing.
It is, but I want to try and make it like, so, okay. So in one sense, I completely agree with you, right? Which is why I constructed this, and which is why I want you to go back and now Google delayed choice quantum eraser and just pick up one of the YouTube videos on this. Especially pick one that says time reversal or something, time causality, violates causality, something like that. There are like I think a billion such videos that come up, okay? I would have played one of them for you, but I don't want to contaminate your young and impressionable minds with that nonsense. But there is something weird about it. Like, it's the fact that I'm able to get interference depending on the choice of the measurement that I make of the recorded electron. But I kind of showed you what I was doing, but like a magician, I kind of, asked you to look in one place while hiding the other place, which is what happened to this guy. I threw away this information, didn't I? All right. So everything I've told you was just look at my right electron. Don't worry about my left hand. Okay. Only look at my right hand. Okay. And that's what I did. I said, look at the interference pattern. I get beautiful interference when I have the right arrow on my recording electron. But what about the left? Well, I get interference there too, but it has this minus sign in it that I was telling you about. Okay, so that is the secret. So if I now plotted the interference pattern for the right arrow, it turns out, and we can derive all this mathematically, of course, but you can see the minus sign right there, and that actually is the secret sauce behind this entire thing. So if I now look at all the cases where I got a right arrow in the recording electron, so I'm just putting that up there, and I'm now looking at the detector, the N on the screen, right? As a function of y, remember y was the coordinate for the screen, I got some interference pattern. And as we have said, we do recover the interference pattern when we measure along the right direction. But if I were to plot now all the cases where I got a left arrow, right, and with equal probability, I'm going to get those when I measure. Okay? And I plot that interference pattern, well, it is slightly shifted. Right, well enough. I can overlap the maxima of this with the minima of that. Does that make sense? If I add these two interference patterns together, I get so indeed it is fake. If I just looked at the electrons and I didn't care whether I got right or left, I will get back my featureless pattern on the screen. That never changes. That has never changed whether I did the measurement up or down or right or left. But what does change is if I only look at the ones where I did right, I get an interference pattern. So there was, all I've said is that in this featureless looking thing, there's an interference pattern hiding, depending on how I partition the data. Okay, and that's all I've said. Okay, there's no retrocausality, there's no backward, moving things in time, space-time, whatever. It's like I threw a bunch of balls on the floor, okay, and I chose not to look at their color for a minute, okay, and they just look like a uniform distribution on the floor, these balls. Now I put on red colored glasses, and I suddenly I see, all the ones that had red happen to be having this strange pattern that is, in this pattern. And all the ones that are blue, let's say, if I now put on blue colored glasses, they all happen to have this other pattern. And if I sum up the two, well, I can recover my featureless plot. Now, that seems very stupid, And it's stupid, but there is one interesting thing. It doesn't matter whether it's red or blue or green and yellow, like I will get an interference pattern. That is the beauty of quantum mechanics, which is it doesn't matter whether I told you about right and left. Well, it turns out I could do like, I don't know, coming out of the board and going into the board, some other basis. Okay. I could have chosen some random choice of basis, as long as it's, orthogonal, as we'll define later on, you will recover these interference effects. Okay. So that is the uniqueness of the quantum entanglement versus classical just red and blue balls or something like that. Okay. Or black and white or whatever. Right. So that is a unique thing. I've just made statements here. So, you don't have to understand or believe everything I'm saying just yet. But that is kind of the unique thing about quantum entanglement. And this is entanglement. Okay. Right here. We have introduced an important concept of quantum computing. Okay, any questions about this experiment and the quantum eraser? And the idea of the delayed choice, of course, is the choice of whether to make that measurement in the right or left basis or the up and down basis can be done at any point in time. And so Wheeler, one of the first, he was a great quantum physicist, a great physicist in general. He had significant contributions, not just in quantum physics, but in general relativity, condensed matter physics, et cetera, et cetera. Okay. So, you have a question?
Does it matter when you choose right or left?
You mean?
Like which branch side measure?
No, it doesn't. Okay. I guess what I'm saying is I can pick a direction in space to measure along. Okay. Which one I get, whether the electrons are right or left, because they can be only in one of two states. They can either be pointing to the right or to the left. But I could have chosen not to measure along right or left. I could have chosen to measure along up and down. Even then, the electrons will always give me only two results. They'll be either up or either down. Okay. If I measure along up, I won't suddenly see right, for example. That is guaranteed by the law of quantum mechanics, by the properties of electrons as well. Okay, it just so happens that is true. But whether I choose to measure in right or left or up or down, that is up to me. That's completely in principle, right? That's up to me, right? I mean, maybe people have argued, actually, that's not up to you. Somehow the quantum system is messing with your brain. It turns some dials in your brain and it makes you pick the direction that will give you this interference result. And this is called the hidden variable theory, by the way. There are people who argue that, we don't actually have a complete knowledge or control of the variables that we choose to measure. But I think, at least to me, it feels like there is free will. Okay, that I have the free will to decide which measurement I'm going to choose randomly. And by the way, these experiments, there are some beautiful experiments. Maybe I can add some links to papers where people have done this with cosmic ray photons, so which were emanated, close to the Big Bang or something like that, and tried to measure these correlations, so that there's just no way that somebody could have known, right? That I'm going to pick these settings here, billions of years later in time or whatever. Yes.
So just to confirm, you do set up your experiment like this.
Yeah.
Two electrons to get the information to the gates. You're always just going to see a featureless plot.
Say that again. Sorry.
You'll always see a featureless plot.
Well, if I just completely ignored what was going on in my recording electrons,
Later.
I just don't worry about them. Keep them aside. Lose them in your home. Whatever. Throw them out in the junk. And if I just measured my electrons that were on the screen, I always get that featureless blob. Right. Okay. Not featureless blob, but like this distribution, which has no interference in it. It looks like the sum of the diffraction patterns from the individual slits. Okay. Just as you would expect for, say, balls or bullets or classical particles, basically. There is no interference. Okay, any more questions on this before I move on from this topic? I thought I would introduce it because, again, this is one of those things, people who do quantum physics, and you may, at a party, somebody may mention this to you. Now you should know what it means and how it's not necessarily an indication that we have abandoned causality. Okay. Oh, by the way, were there any questions on the Zoom? Wasn't paying attention. A couple people. I guess I was watching this on Zoom.
Yeah, no.
Yeah, let's go back to our presentation.
I didn't have a question. Hi, Professor.
Then, is that on Zoom? Is that, by
Yes.
the way? Oh, yeah, yes, go ahead.
Yeah, so I don't have a question. I just have a comment that it was a little bit hard to follow that discussion because the camera was panning over like right, left sometimes. So it's very hard to follow the discussion.
Yeah, I mean, I think it tries to follow me around.
Yeah.
I don't know where you're seeing right now. It tries to follow me around, but I don't think it's perfect. Were you able to see the board?
Yeah, somewhat, not everything though.
Not all of the board, I see.
Yeah.
Yeah, was it to the extreme left that was missing, basically?
Sometimes left, sometimes right, but we couldn't see the board completely
Yeah,
sometimes.
maybe it has to do with how far away this is, but I can't move it super far because of where the computer is. Maybe now it's a little better. Or I'll try to write more to the middle of the boards, maybe from future.
Okay,
But thank
sure.
you for pointing that out. Do you have a question based on, I can show you the board again, maybe that will help. All right. Are you able to see the board any better?
No, right now it's okay. Now, yeah, now a little bit, but it's showing you mostly.
So you can't see the board, is that what you're saying?
No. Yeah.
Okay. If I go closer to the board, then I guess it focuses on the board now.
Yeah, but only the center. I don't want to disturb the class. Please continue.
Okay, yeah, sorry. It's just, this is the best we can do with this available technology. Already, I guess, better than just my laptop camera, which is what I have here. Okay, so let's move on. So we've talked about this, and by the way, I should mention that the person who came up with this idea at the time when he came up with it, he was actually like Wheeler, who's a very great physicist. He was Feynman's advisor and so on. He was sort of very much, sort of propagating the view that this is somehow evidence for the role of consciousness. That, like the fact that I can choose when to make the measurements and that recovers interference is somehow a hint that consciousness has something to do with measurements. Okay, so that was his sort of theory, at least that quantum mechanics maybe is for the first time we are having a theory of physics that actually involves consciousness as being important to the experiments, which is something, of course, Einstein hated. The idea that we could somehow, affect the results of an experiment or something. He just thought we weren't that important to be, affecting physics to that extent. Okay, so by the way, yeah, I should mention this, which is that everything I told you with electrons has been done. These experiments, the quantum eraser and all that has been done, but not with electrons, with photons. Okay, and the way in which they did it is instead of taking electrons, they took single photons. The single photons, instead of going through a slit, which of course they could have done it with a Young's double slit, but it was easier for them to send it into something called a beam splitter, which transmits half the electrons or reflects half the electrons. Well, if you have, electrons, I'm saying, photons. And of course, if you take a single photon, then you have to ask, what happens to the photon? Well, obviously, in the quantum picture, it has a state where it can either be reflected or transmitted with equal probability, and we have to write that as a state vector in the state space, which is slightly.
Professor?
We'll come to this point again and again. It's different from just saying, I'm just flipping a random classical coin and deciding whether the electron goes up or down. That, of course, is the obvious answer. Where you say, well, I don't know, but it's just a statistical problem. But it turns out, because of effects like this quantum eraser, we can rule out those effects, actually. the fact that, we can just randomly flip the coin and decide whether the electrons went up or down or right or left, etc. Okay.
Can you
and,
please
to
share
construct
the
like
screen?
this double slit experiment, we now take this beam splitter and we have another beam splitter, okay, two beam splitters. And the idea is that we take the single photons, we don't need the mirror, strictly speaking, to understand the experiment, but it's just helpful to redirect all the beams. And now you can see there are two paths, right? The electron can go either this path or it can go this path and come and recombine here. And the question is, whether it goes up or to the right or the left, that is decided by this interference between the two paths, the down path and the up path, for example, at this first beam splitter. Okay, and the measurement of those detectors can be give us an interference pattern, for example, by varying sort of the length of this interferometer. So that's how we can get the interference fringes. As we vary the length of the interferometer, will give us interference fringes. If I just observe the counts on one detector, it'll get, I'll get the interference fringes. As I vary the length of the interferometer, or I can just look at the two different detectors and I can find that one of them will be at a maximum when the other is at a minimum, and so on and so forth. Okay, so this is the equivalent of the Young's double slit, but just done in a way that is more easy experimentally to carry out and to vary all the things very carefully and so on. It makes the experiments a lot easier, basically. Okay, I don't remember why.
Can you please share the screen?
I guess one of the things I wanted to point out is that this is similar again to how do I measure whether I'm in path 1 or path 2, slit 1 or slit 2? It's as simple as putting a beam block in, right? So if I put a beam block in, then whether I have the block in this arm or this arm tells me whether when I get a click on the detector, it tells me whether I'm in path 1 or path 2, right? That is clearly going to tell me that I was in one of these paths. So this is a classical way of observing where the photons, which path the photons went to. And you can see that, there will be cases just like we had in the case of the electrons, where by putting the block in, I'll increase the counts in one of the detectors rather than decrease them. Because, for example, let's say I set everything up before I introduce the block. So prior to the block, let's say that I had perfect constructive interference in the detector P1 and perfect destructive interference in the detector P2. So there was maximum counts in P1 and minimum counts in P2, in principle 0 counts. Now I put the block in. Now the photon cannot take this path, it has to take only the bottom path. And now when it comes to the beam splitter, it has half probability to go either up or to the right. Okay, which means that now I'll get clicks sometimes in the detector as I do the experiment, which earlier I had 0 counts. Similarly, here I have maximum counts, much higher than the counts that I'll ever see from just having one of the paths. So I'll get more counts in this detector sometimes when there's no block rather than when there's block. So we cannot again explain this by saying that somehow the electron goes through both paths, circles around multiple times, figures out what everything is happening before it hits the detectors, right? Because when I block the path, I can get both increased and decreased counts in the detectors. Same idea, just like with the other. Okay, so this experiment, which is called classical eraser, which is just the question of when do I put that block in to decide whether I'm in path 1 or path 2. That's a classical decision, right? It's just made by a signal, which it's coming from my brain to my hand to decide to move the beam block in or out. Okay, well, you can also make that decision of when to do that, okay, by using some random signal. For example, you can have like some random, number generator, for example, or you can have some random switching signals that are coming out of some electronic circuit. You can have, whatever, any number of ways are possible for you to decide whether to insert that beam block in or out. And the actual experiment, of course, was not quite as simple as I have sketched it, but they did something very similar. They took, in fact, this is a qubit that I work with, which is called the NV color centers in diamond, and they emit single photons. Okay, and these photons were then sent into a beam splitter, sent along, this path 1 and path 2, as you can see here. And then the decision of whether to insert that beam block or remove the beam block, which basically in this case, they inserted or removed a beam splitter. Okay, it's, again, little details, which we don't need to worry about. was done much later. It was done well after the electrons had gone through, the photons had gone through the first beam splitter. And so again, you can ask, well, was there some effect of my decision which happened after the photon went through, which made it decide now that it's going to go through both paths? Because that is the question that, you can ask. You can say, the fact that I inserted the beam splitter after the photon already went through the path, through the beam splitter, and yet I'm recovering interference. Again, the same idea of this classical, of this eraser experiment. The which way information can be decided whether to observe or not to observe well after the experiment has basically been done, you can say, in some sense. Again, the exact same arguments that we talked about, you're basically throwing away the other parts, right, where you don't observe that. And if you then took both of those informations into effect, you would see exactly they match up out of phase with each other, and the two together will give you back no interference again. So that all was verified by this experiment. But exactly, this is it makes for a nice. This is why this experiment, even though in principle we understand it perfectly well, and we know that there's no mystery, it made it into Science. Science, which is one of the premier science journals, right? You write a paper to Science if you have made some really new advance in physics. In some sense, there was no significant advance in terms of our knowledge, but the fact that we could do the experiment and show the results and prove that everything from quantum mechanics works at the level of a single photon, and to do it in a way that's very controlled. Because people were always able to argue, well, maybe there were experiments that were done, by the way, in the 1980s by Alain Aspect, which were very similar to this. And he got the Nobel Prize in the 2019 or 20, something like that, for those experiments that he did in the 1980s. But he did them, in such a way that people could always make some argument that maybe those experiments didn't completely get rid of all the loopholes, when the decision was made. Because, he didn't have the technology of computers that could generate those random numbers quickly enough and all that stuff. That was all taken care of in this experiment, for example. And the results that he observed were still seen. Okay. I should also mention this famous experiment. This got into Nature 2007. This was a much harder experiment because this was done actually with the way I described it, okay, which is an entangled state was created. So basically the photons were sent through a telescope. The telescope was set up, these entangled photons propagated 144 kilometers, or single photons propagated 144 kilometers from the island of La Palma to Tenerife in the Pacific, okay? And these experiments, or maybe it's in the Caribbean, I can't remember. Yeah. So you can see here, this is a pretty major experiment to have to set up single photons. And again, the reason for the distance is to make sure that the choices of the settings on the interference measurement experiment, the choice of whether to erase or not to erase the experiment, the which way information was made in such a way that it couldn't somehow propagate back it would be sufficiently long distance that light could not tell you that. Because maybe there's, people argued, well, maybe there's some secret way in which that choice is actually that information is coming back and telling you whether you'll see interference or not. And the way to remove that is to just separate them by such a large distance that there's no way that even light could make it there in the time that it takes for you to do the measurements. Okay. So these are all the typical loopholes that you have to close in these kinds of experiments. That's what makes them more challenging. You can see, they had GPS clocks to synchronize the time so that they know exactly at what time they made the measurement setting and all that. Time tagging of the photons, the way in which the which way information is erased for photons is basically again using beam splitters and polarizers and things like that to do this. So I won't get into the details, but it's a beautiful experiment that you're welcome to look at and read on your own. Which obviously you don't have to follow every detail to understand what they did now because you have some knowledge of the principles they're testing. But yeah, and the point again is this quantum eraser experiment did indeed yield exactly the results we were talking about. But when they looked at up or down, they were observing no interference. But when they decided to switch the measurement basis to right or left, they recover interference if they look only at left or only at right. But then, of course, if they combine left and right together, they recover the fact that there's no interference. So in the end, the results were exactly in prediction with quantum mechanics, but it was kind of, again, one of those really cool experiments that people publicized a lot in Nature. Okay, awesome. Well, I guess it's nice to spend time talking about these things, even if they don't strictly matter to quantum computing as much, but it's important to have these sort of experiments in the background. And I think the mystery that I would like to always tell you about, and this is the fundamental mystery, this is what Feynman has already pointed out is at the heart of this problem, is the fact that we have to describe the evolution of these particles, the experiments, using this wave-like picture or this state vector picture of the state of the system, using like those kets, those states that I wrote about, or the state vector in a Hilbert space, or just if you go back to the older picture, I had to think about this as probability waves spreading out through the system, and so we had to describe the experiments using that wave picture of the Schrodinger wave picture of the probabilities. But when we actually observe the particles, when the particles actually are observed at any location, they always register as a single point, even though where they could be, the sort of the space over which they could be, all of that space is described by this probability wave function, and that is somehow correlated across all of space and time in such a way that you will get the measurement results as predicted by this theory, even though at any given time the particle itself always registers itself at one location in space, right? So that mystery is still there. All of these things I've told you about, are just making that mystery a little bit more, what's the right word for it? Or making that mystery sharper, or giving you some ideas of like, okay, you can say, oh yeah, okay, it's cool that, sometimes you observe them as particles and sometimes you observe them as waves. Okay, it's fine. But now we are starting to see how that can play some games with our ideas of causality and locality and effects and all those things begin to sort of, affect our thinking about that. Our classical brain is not able to understand how it is possible that an electron over here can somehow know what happened to an electron that was somewhere else, or that was recorded many years later, or something like that. Like, how is it possible that we could suddenly recover these various types of effects? Yeah, so that's all I would say. That is still a mystery, and I have no way to tell you why it is this way or how to think about this. All I can say is this is how nature behaves, right? And at some level, we just have to accept that doesn't behave the way that we would like it to behave, where we can put it into these boxes of like particle waves. We have to accept that quantum mechanics has this weird behavior. And that is, again, the Feynman central mystery of quantum mechanics. And later on in the class, I'm going to tell you about another experiment, which is called the bomb experiment. And later on, we'll talk about that. That also, I think that's even more sort of brings out the paradox of quantum mechanics even more, in some sense, than even the delayed choice quantum eraser experiments. But we'll talk about it. It's at this rate, maybe a little later in the weeks than I had planned. That's okay. Okay, so coming back to, again, this is just purely, philosophical sort of ideas. Like, people have various interpretations of what's going. This fact that, as I've just said, that somehow it looks like there's a wave, but then when we observe it, it's a particle. People have had debates about like, how is that possible? And the one interpretation, which is called the Copenhagen interpretation of quantum mechanics, is that a particle, these quantum objects do not have anything definite about them. Like, there's no property that's definite. Every property has to be described by this wave function or state vector. And so the particle is simultaneously in all of these locations. And we call that the superposition. And the waves are the probability waves or Schrodinger waves, whatever you want to call them. But when we observe them, they collapse into one of the places that we observe. But of course, again, this is where people get very confused. They're like, what does it mean to observe? And I've tried to give you a flavor of that. Like, entanglement is a way in which you can, for example, observe something. Because when a particle gets entangled with something else, it effectively leaves some information with that other object. Okay, and measurement is just a sort of a entanglement, but just taken and amplified to a classical level, basically. Again, I'm just waving my hands here, but this is one way to think about measurement. But the question of when does it go from being just entanglement with another particle to being a measurement, that is still a little bit of a fuzzy area. Like we can't quite say yet when is it clear that something is a measurement versus when is something just an entanglement. Okay, that's something that's very interesting topic. There is a decoherence and entanglement and measurement. These are all like bound together in quantum mechanics in this weird way and unique way. And we are still trying to like make that all more less fuzzy in experiments, for example. We can certainly say something about it in theory, but it's a harder question to decide experimentally when one is true or the other. Usually you can say, I'll know it when I see it. Okay, that's kind of like one of the ways in which we argue about these things. Is I'll know when it's a measurement when I see it, but of course, that leaves something to be desired. Okay, so this is one approach. This is the Copenhagen interpretation, and this is what I just said. Who has to observe it? When is it a measurement? When is it just an entanglement? When is it a decoherence? Whatever, right? I mean, so this is still a question that people argue, right? And of course, one of the famous arguments about this was the Schrodinger cat experiment, which I'm sure you all heard about, right? Yes, everybody has heard about. Yeah. So the Schrodinger cat was that the cat is in this box. If you haven't heard about it, I'll say it. And there is a box, and there's a poison gas in this beaker, and the beaker has a hammer that is over it, which will, or maybe not a hammer, whatever it is, that will break it and release the poison gas. But the choice of whether the beaker is broken or the fact that the hammer comes down on the beaker is made by the decay of a radioactive atom, a single atom. Okay, and you could replace that by whether a single photon is emitted by a photon gun or something like that. Whatever you want, some quantum effect. Okay, and because of a quantum effect, we can only assign like a state of the system. We cannot say for sure which. So we have entangled the state of the cat being dead or alive, effectively, with whether the atom decays or does not decay. Okay, so that's how the superposition of this system must be written, as long as we don't open the box to observe the cat. When we open the box to observe the cat, and we see that it's dead, we then know that the atom must have decayed, for example. Okay, so that's one way to ask this question, but of course, then people were like, wait a minute, so you're telling me that the cat is both dead and alive? This is where the famous sort of interpretation questions come about. And I should mention that this is something that people are exploring in experiments, okay? So, one of the questions we can ask is, when is it that something stops behaving like a quantum superposition and becomes like a classical dead or alive cat, So can we make bigger quantum superpositions, bigger quantum cats, quantum kittens, if you like. Okay? And so, for example, here is a bunch of experiments that people have done. I kind of mentioned this. People have taken like molecules that look like this and sent them through like a double slit experiment to observe the interference fringes. Well, it wasn't a double slit; it was many slits, but the idea still remains the same. They've sent things like neutrons. They've sent atoms, clouds of atoms. They have sent, this is neutrons, this is clouds of atoms, this is molecules, this is superconducting rings. So in superconducting rings, in a superconductor, as you may have heard, there are these electrons that move without any loss of, without any resistance, right? So a superconductor is infinitely conducting or has zero resistance at the superconducting transition. And so one can set up these systems where there are electrons circulating in a ring, and as we know, the ring, if the electrons are circulating, they can last effectively forever. Okay, the electrons can keep circulating. And one of the experiments that people have done is set up in such a way that the electrons could circulate either this way or that way, and they don't observe which way it is, or they can observe that by using some magnetic flux detectors, and that allows them to then say, yes, now the ring has to be described by superposition of clockwise and anti-clockwise current. So that's again like a interference experiment as well, and they've observed those macro. Because it's thousands or millions of electrons, you can think of that as a macroscopic superposition. And there's a way in which we can characterize how big the superposition is through this macroscopicity parameter. And this is sort of like a graph of like what has been observed into the late 2010s. I should probably try to find more newer data to update this graph, but at the moment, we're somewhere. I should tell you that the scale is logarithmic. So going from say 8 to 10 is a 2 order of magnitude increase in the macroscopic size of the superposition. So that's like 100 times bigger superposition to go from say 8 to 10, 10 to 12, etc. Those are fairly big superpositions. Let's deal with this cartoon. The cruel experimentalist who could be shooting our cats double slits would not be very nice. Would not get approved by the IRBs for biological experiment. So I'll leave you with another theory, which is also very famous, and you might have heard of it, which is called the many worlds theory, which is that instead of thinking about this collapse and wondering about when the collapse happens and all that, the many worlds or I don't want to call it multiverse because that has a slightly different connotation, but the many worlds interpretation of quantum mechanics says that actually both of those possibilities happen. Okay, it's just the branch of the wave function that we are on is the one where we may observe the cat to be dead or we may observe the cat to be alive. But there's another branch of the wave function completely in accordance with the laws of quantum mechanics, Schrodinger equation, whatever. In that branch of the universe, the cat has stayed alive. In our universe, the cat might be dead. Okay, and so then there are questions of like, okay, how can I reconcile that with actual experimental measurements? Because you may ask, there was that bone rule, like we do observe whether sometimes the cat is dead, sometimes the cat is alive. Can we predict all those things? So so there's still work to be done on reconciling the theory, and I think there's like very good work being done by various people. So it's entirely possible we can reconcile using the many worlds theory all of this stuff. Okay. And for most scientists, it's probably more like this, right? I don't know, man. We'll just go ahead with our day-to-day, we'll calculate, we'll do our experiments, and let's see what we see. That's kind of probably the attitude of most physicists who don't work on this or think about this every single day. But I think it's something we should be thinking of. It's like one of those things that should puzzle all of us. Okay, I'm going to stop there. And we will continue next time. I guess, I'll just say this last thing. Oh, sorry, you can't see the slide. Which is that then the reason why people have that, shut up and calculate is the famous, sentence that people say, is because we know the laws of quantum mechanics allow us to do all these amazing things, which I kind of referred to in the very first lecture, which is we can use these predictions of quantum mechanics to build all these amazing technologies. So even for people who don't care about quantum physics, they should care about quantum physics in a way, because it has allowed us to make all these technological achievements, and of course understand the universe with quantum field theory and particle physics and astrophysics and quantum computing, as we are going to talk about in this course. So this is probably my last sort of reference to the mysteries of quantum mechanics. We'll come back to some of them as we talk about like qubits and stuff like that, but from now onwards, we'll be more into the course. So, but if you have any more questions about the weirdness, the quantum eraser and other things, feel free to come and talk to me. I can also give you some more references for reading and stuff if you're interested. So if I hear from you, many of you saying you want to read more or something, I can give you some references. Okay, yes, I'm done. Thank you. Yeah, have a good weekend.